All right. Can you guys hear me in the back? Am I good here? All right, let's get started. Hey everyone, welcome back to Data 100. We're now on week 6 out of week 8, which means we only have 2 weeks of class left, right? And then on week 8 we have all of our final reviews as well as our final. So we're in like the home stretch of Data 100, and I hope you guys are excited for what we're going to cover, because at the end of the class we kind of put together all the stuff that we've been learning throughout the summer and try to tie it together in some cool and interesting ways. And so today we're going to be talking about logistic regression, and I've originally planned to talk about logistic regression for 2 lectures. So the original plan is to cover it today and tomorrow. After looking through the slides and preparing the lectures, I suspect it may go 3, depending on how well you guys can understand the material and how well I guess I can present it as well. Okay, so again, as with linear regression, because logistic regression is a pretty central topic and model in this class, I really want to make sure that you guys can get enough time and practice with the material in order to feel like you understand it well. Okay, so if you feel like I'm going too fast today or tomorrow, do raise your hands and ask me to repeat the slide or repeat like my demo. All of that is totally fair game. And again, I suspect, as with linear regression, it will probably take a few times of practice and like some number of hours for you to like wrestle with these topics in order to really understand it. Okay, so if you feel confused after today, I think that's totally normal. And what you should do is I'll try to give you some pointers on how you can really develop your understanding of the material after you go home or work on the problems during lab or discussion or in the project. Okay, so homework 6 is due tomorrow, and project 2 will be out Tuesday. So homework 6 is our last real, like what we call a homework for this class. In this class, projects are essentially longer homeworks, but we do have, from now on, projects for this class. So we're going to have project 2 coming out tomorrow, and then project 3 coming out the week after that. Okay, so 2 more assignments, but both of them are pretty cool because they're the first relatively open-ended assignments that we'll have, and they should hopefully give you a feel for what it's like to start from scratch and work on a problem from start to finish. All right. Let's talk about classification. Okay, so classification is a type of prediction problem. In classification, we try to make a model that makes a prediction about a categorical variable. For example, my favorite basketball player is named Kawhi Leonard, and you might ask the question, if he takes a jump shot against his team, will the jump shot go in? You could also ask, a 21-year-old white female is arrested for assault a second time. If left free, will she be arrested again? And this in particular is a question that people have asked when designing what's called the compass algorithm for recidivism. So people are trying to decide whether certain types of people are more likely to get arrested again for committing crimes. And it turns out that this is a topic of much controversy, as you can imagine. But again, it's a type of classification problem. And in this particular problem, the outcome of your prediction has more severe consequences than perhaps whether a jump shot goes in. Okay. And it turns out that classification and regression are pretty closely related. In both classification and regression, we have some labeled training examples that I'm going to delineate with X and Y. We fit our model on those training data, and we try to apply our model to some unlabeled data. The assumption underlying both types of models is that the unlabeled examples have similar results or similar labels to the data that we've already seen before. Right? So if this assumption doesn't hold, then there's no real reason to use our training data, because whatever we do with our training data won't generalize to more data. After we fit a model, we usually have the following questions. We want to know whether the association between X and Y in the training data are representative. We want to know whether we have enough training data to begin with, or whether we should collect more. And perhaps most importantly, we want to know whether our model would generalize. Okay, so whether it would generalize and make accurate predictions about data that we haven't seen before. Okay, so I suspect after the weekend you may have forgotten everything that we covered for linear regression, so let's cover it real quick. Okay, so in linear regression, our goal here is to predict y from x. And what we're doing here is we're trying to estimate what we call like the generating function or generating model for our population, which I denote with f star of x. Okay. And in linear regression, what we do is we assume that in the population, there's a linear relationship with what we call like theta star and x. Right? So we assume that there's a linear relationship between the features that we're interested in and the outcome that we're trying to predict. All right. And so what we do is we say f of x is equal to theta dot product with x. And our model is essentially all the types of models you can get from changing theta. Okay, so in linear regression, we set this as our model. And what we do is when we run gradient descent is we try out a bunch of different thetas until we find the best theta for our particular data. All right. To fit the model, we select a loss function. And by now we've covered a few. We've covered mean squared error. We've covered mean absolute error. And we've covered different modifications to the loss that we called regularization. We've covered L2 and L1 regularization, which are known by ridge regression and lasso regression, respectively. Okay, but in all of those cases, what we do is we pick a loss function that we think is appropriate, and then we minimize it. Darn, that was supposed to appear. It's fine. Okay, so let's. Oh, okay, hello. So the squared loss for linear regression is y minus theta dot product x squared. And what we wrote down is we say, okay, well, if we have some observations, x1 through xn and y1 through yn, then this is our average loss, our average mean squared error loss for a linear model. When we introduced regularization, what we said was we can add a term to the loss function that encourages small theta. So in other words, we'll increase the loss when thetas are large. Okay, so quick recap of linear regression. And the reason why I want to recap this is because logistic regression is very closely related to linear regression. All right, so let's talk about classification. The basic idea, what I want to do right now with these next few slides is show you that classification can be framed as a type of regression problem. Okay, so in regression, what we're trying to do is predict a numeric outcome from some data or from some features. And in classification, what we're trying to do is predict a categorical outcome from some data. But what we can do is say, okay, instead of predicting the category, we'll predict the probability of a category. And probabilities are numbers. And so now we have a problem that's more closely related to regression. So, in classification, we want to predict a categorical y from the features x. And the difference here is that y is in a fixed set of possible categories. So if we're looking at whether a basketball player will make a shot, we can say that y can be either make or miss. Okay, and what we'll do is we'll assign numbers to each category. So we can say, okay, if you make the shot, we'll code that as a 1 in our data set. And if you miss a shot, we'll encode that as a 0. But this feels a lot like, okay, so we have two classes here, which makes it what we call a binary classification problem. And the thing that we know here is that this feels like a random variable, right? And in particular, it feels like a Bernoulli random variable, because a Bernoulli random variable can only take on values 0 or 1, and it takes on the value 1 with some predetermined probability. Now, it's not exactly a Bernoulli random variable, because the probability P is dependent on X. So for example, if a basketball player takes a shot really close to the hoop, you might guess that that person will make the shot more often than if he takes the shot from like really, really far away. Okay, so it's not exactly a Bernoulli, but it is, we can consider it a Bernoulli if we say that P is dependent on X. Okay. And so what I'll write down now is if I say capital X and capital Y for this slide and the next slide, we'll say that this is a point drawn from the population. Okay, so it could be one particular shot of a basketball player. It could be one like MRI scan looking for something wrong with the brain. Okay, so what we have here is 1 point drawn from the population, and x is our features, and y is a true value, and these are a pair of random variables. Okay. And we might be interested in what we denote by expectation of y given x, which translates to, if I happen to know the features, what will y be on average in the population? So this is a statement about the population. This says, in real life, what is my best guess for y if I know these features about that particular shot, that particular brain scan, the particular weather pattern for that day? Okay. One thing to note here is that this sort of notation also applies to linear regression. If you look at the slides from previous semesters of the class, you'll also see this expectation of y given x. I've waited until now to introduce it because I feel like it applies. I feel like it makes more sense to apply it to classification. But you can also ask the question, what is expectation of y given x for a regression? And actually, nothing about this statement here will change. For regression, the expectation of y given x is a numeric property. In classification, it's a value between 0 and 1 in this particular case. Okay. So when I say f star of x, you can also write it as expectation of y given x, and usually those two things are equivalent to each other. But in general, I'll try to use f star of x more often because that's the way that we've done it first, and so I'm just trying to be consistent. But I will tell you that you will see this pretty often, especially if you go more into the statistics land. Okay. Beings are appearing in all sorts of orders. Okay. So, all right, we have expectation of y given x. Okay, so I can do a little bit of calculation here to simplify it. So since y is a Bernoulli conditional on x, the expectation of a Bernoulli is 1 times the probability of 1 plus 0 times the probability of 0. And this is a formula for expectation if I just add a given x here, which essentially means that the probability depends on x. Okay, so I have here 1 times the probability of 1 plus 0 times the probability of 0. And this 0 makes this term go to 0. And so what we're left with is a probability of 1 given x. Okay, and I told you before that we also write expectation of y given x as f star of x. Okay, so what we can say here is that if we fit a model, we can fit a model that predicts how likely is a 1 going to appear given an x. In other words, given that Kawhi Leonard is like 50 feet away from the basket, what's the chance that he makes a shot? Given that he's 2 feet away from the basket, what's the chance that he makes a shot? Given that like a scan reveals like these patterns in the skin or in the image, what's the chance that you have like skin cancer? Those sorts of things. Okay, so we want to estimate with our model the probability that y is 1 given x. And this is a numeric variable, but it's not completely numeric because it's a probability. Right? So we can't have probabilities that are lower than 0 or greater than 1. But the idea here is that we can tweak regression to predict probabilities instead of just any number. Okay, so while linear regression predicts any number from negative infinity to positive infinity, the idea here is that we can tweak regression a little bit to predict probabilities instead of any random number. Okay, so in linear regression, we have this model, which is f of x equal to theta dot x. And in logistic regression, we have a similar model, but we'll tweak it a bit with this function that we call sigma, or the sigmoid function. So it looks a lot like linear regression. So this part right here is exactly the same as linear regression, but we have a small tweak. Okay, so let me give you some intuition for this particular function. All right. Today we're feeling like the NBA, so I have here some NBA data. And what I have here is a data set containing NBA games. And I have here one row for every game that was played between two teams. All right. To show you more of this data, I can do a little interactive thing here. Okay, so we have here 2,000 rows and 29 columns. We see here the game date. We see here whether the team won or lost. We see here how often the team made shots against the other team, so on and so forth. So we have a bunch of columns here. And maybe what we're interested in predicting is whether or not the team won, depending on how many shots they made. So we might suspect that if you make a lot of shots, you'll probably win. If you miss a lot of shots, you'll probably lose. Okay, so, and it looks like we have here data from 2017 all the way to 2018. Okay, all right. Let's take a look here. So what I'm going to do is take the win-loss column and encode it as 1 or 0. So I have here this line here which encodes the strings as 1 and 0. And what I can do is make a plot of the field goal percentage versus the won column, like so. Okay, what are we looking at here? We have here the field goal percentage on the x-axis, which says if you're higher up on the x-axis, your team made more shots. This is the proportion of shots made. And on the y-axis, we have here whether the team won or lost. So a 0 means the team lost, a 1 means the team won. But because values are only 0 or 1, we have overplotting. And so what we can do is jitter the points a bit. Let's jitter the points. And we'll jitter the points just by a little bit, like that. Okay. So we can see here that if you fit a linear regression, like as is to this data, you'll get this sort of pattern, which sort of makes sense, right? So it's kind of like what we expected in that if you make more shots, you'll win more often. But this is not super great because this line is not bounded by 0 and 1. So if you go like below, if you go down here to like negative, to like 0.3 field goal percentage, you're going to predict that people won like negative 0.2 of the time, which doesn't quite make much sense. Okay, but what I can show you is, let's see. Okay, well the first thing I want to note here is that this field goal percentage is maybe not what we're most interested in for prediction. Right? So it could be the case that if like two teams that are really good at shooting like face off against each other and both teams just make a lot of shots, one of them is going to end up losing no matter what. Or it could be the case that two teams that are really bad at shooting play each other and one of them is going to win no matter what. And so what we might be more interested in is not the field goal percentage of a particular team. Maybe what we're more interested in is the differential, right? So how often or how many more field goals did one team make over another team while they played? Okay, so to make that happen, I can do some data manipulation. So I have here my data frame. I can pull out the team name, the game ID, the field goal percentage, and whether the team won or not. And we see here that every game in this data set appears twice, one for the home team and one for the visiting team. And in this case, it looks like the Rockets beat the Warriors, even though the Warriors made more shots. And so what I want to do is I can group together the table by the game ID and subtract the field goal percentages from each other. All right, so let's make that happen. Let's do that. So let's group by the game ID. And what I want to do here is take a look at how many, I can do pairs at size to see how many games there were for every game ID, and let's say there were 2, one for a home team, one for a visiting team. All right. And I can take the first team in this data set and join it with the second team. Do this so that we get what we get and a column for opponents. And I think there's no underscore here. My bad. Okay. So if I do this, I have one game ID for the Celtics versus Cavaliers, and I have here the Celtics field goal percentage and the Cavaliers field goal percentage. Okay. So now this lets me subtract out these two. So call this the games table. And what I can do is take the games table. I can take, I can get rid of this column because I had the one column, and this column is redundant with this one. So let's drop the one opponent column. Like so. And then we can make a new column called field goal percentage difference. And this will be the field goal percentage column minus the field goal percentage column of the opponent. And there they are. Okay, so we have this new column here, the difference between this team and that team. Okay, so now if you plot, let me just take my code here, paste it down here, swap out my data frame, and I'm going to plot this column, which is the difference. So the data here are a little bit better separated in that there's less overlap on the y-axis. So it turns out that if you make 10% more shots than your opponent, you're probably going to win. If you fail to make, or if your opponent makes 10% more shots more than you, you're probably going to lose. And in between, it's a little bit hard to determine. But what I can do is, you would suspect that, if both teams make around the same number of shots, the chances of them winning are probably about 50-50. If one team makes a little bit more, like a few percentage more shots than their opponent, they're more likely to win. And so we expect like this gradient, or a gradual increase of probability of winning. And so what I can do here is I can make slices. I'll slice out the data into bins, and then take the average y value at each bin. So for example, if I go take the bin from -0.1 to 0, I'll take all the points that lie in this bin and then find the average. Okay, so I have here the code to do that, which just bins the data. And what I've done here is I have binned the data, and at every point on this line is the average y value for each bin. And what you can see here is that there is this gradual increase, and it has a very particular shape. It has this S-curve shape. And this S-curve shape arises because as you make or miss more shots than your opponent, you have essentially like a gradual increase from losing to winning. Okay. So here is something that's also interesting. So here I have a win rates. I have the win rate series, which has the win rates for every single point, every single bin that I have on the x-axis here. So it goes from 0 to 1. If I divide by 1 minus the win rate, this is what we call the log odds. Okay, so this is the probability that A happens divided by the probability that A doesn't happen. So this is the odds ratio, not the log odds, sorry. There they are. And if I plot this, we get a plot that looks like this. So how do I interpret this? I interpret this as saying, if I make 10% more shots than my opponent did, then I'm 50 times more likely to win. If I made like 10% fewer shots than my opponent did, my opponent is probably going to win. They have a much higher chance of winning than I do. And so we interpret the y-axis here as like kind of the odds of winning, and the odds of winning are how many times more likely am I to win than my opponent. Okay. This is the odds ratio, but it turns out that if I take the log of this, so if you remember way back from when we did transformations, we can take the log of a plot to try to get a linear relationship. And it turns out that we get a linear relationship in the odds ratio. Okay, so this is a curious phenomenon. And it turns out that what we often assume with probabilities is that the log odds ratio is linear. Okay. And so what I'm going to write here is this. So we know this relationship, and it turns out that this relationship often holds for like values involving probabilities. Not always, but often. Okay, and so what we're going to say here is, okay, well, I can't fit a line to my original data, but I can fit a line to a transformed version of my data. Just like how when we talked about transformations, if you fit a line to a transformed version of data, you'll fit an exponential model or a polynomial model to your original untransformed data. And in this case, what I'm saying here is this particular transformation has a linear relationship. Okay, so I have here the log odds ratio of winning and losing has a linear relationship in theta. And it turns out that if I go through some algebra, and this notebook will be available to you so you can go through the algebra yourself, I can like take the exponent on both sides and simplify, move stuff around. Okay, and what we get at the very end is we have, if you solve for p of y equals to 1, we have this formula right here, which is 1 over 1 plus e to the power of negative x dot theta. So this exponent here is an abbreviation for e to the power, and I just use it so that we don't have like super small like text right here. Okay. Any questions about this so far? Yeah, Sophie?
What's the t?
What is the t?
Yeah, is it x or like sigma is a function of t? So what is it in this?
Yeah, so it's a great question. So what is t referring to here? So this particular formula here is a form of what we call the logistic function or the sigmoid function. Okay, and the sigmoid function says if you pass in a value t, I'm going to return to you 1 over 1 plus e to the power of negative t. And so for this particular, when you make that linear assumption between x theta and the log odds ratio, what you'll do is you'll plug in x dot theta into t. And so you'll see that these two expressions are exactly the same, but the t here is replaced by x dot product theta, which essentially means we pass in x dot theta into this t here for this function. Okay, so to give you another angle on this right here, it just happens to be how the algebra works out, but it turns out that this particular this particular expression has a name, okay, and the name is a logistic function, and what happens is this outcome right here is similar to the logistic function if you pass in t. Okay, and so if I code up this sigma function, so let's call this sigma, and we'll do 1 over 1 plus np dot exponent negative t. So this is e to the power of negative t here. What I can do is take, let's see here, I can take, let's do diffs, take my win rates, and what I have here is simply just the bins that I've created before, and I can take my win rates and plot them. So here are my data. So here are my data values that I've binned together. I'm taking the average for every bin. And if I plot on top the x values and the sigmoid of the x values, if I do this, I'll get a curve that doesn't quite fit the data, but if I multiply by 30, it fits the data quite well. If I multiply by 20, it doesn't fit so well. If I multiply by 50, it doesn't fit so well. It just so happens that 30 is a good number that happens to fit this data quite well. Where did I get 30? You get 30 if you get the number 30 if you run logistic regression. It's the coefficient theta that goes into here. So this number is magical for now, but just like with linear regression, once you fit the model, you can pull out this number 30 whenever you want. Okay, let's take another look. Let's take a closer look at this sigmoid function. All right, so I'll run this, which plots the sigmoid function for several different values of theta and x. Okay, so what do we notice here? We notice that when theta is negative, the sigmoid function goes from high to low. When theta is positive, the sigmoid function goes from low to high, but the function is always between 0 and 1. Also, when theta gets closer to 0, the function slopes up. The function has a smaller slope in between, like the small region here around 0. And when theta is large, there's a higher slope right here. Okay? And so, if you remember way back from my slides, I said that the logistic model is the linear regression model, but you pass the output from linear regression through the logistic function. And so what happens here is you can see that no matter what value you pass into the logistic function, you get a value that looks like a probability. And the reason why it looks like a probability is because we made some assumptions about probability in order to get to this formula. Okay, so these numbers here are valid probabilities because they're always between 0 and 1 as desired. Okay. Here we go. Let's take a look here. All right. You know, I forgot to include a break. So why don't we take a break now? And what I'll do here is I will pull up the attendance form and open it. Let's do that. Okay, and then the URL is bit.ly/@d100. Does that make it a link? There we go. All right, cool. So let's fill out attendance and come back in a few minutes. We can fix this for now by removing this line right here. That one right there just commented. I think things should work. I think I assumed that there was a package installed that wasn't installed. So what I should do is contact the people running the hub and tell them to install the package. No, it's fine. I'll contact them. I'll just let them know. Here we go. I know a little. I know like the bare basics of it.
For funsies? Or is it gonna kill?
I hear that from what I hear, they're not too difficult. Sounds like a fun class if you want to take a fun class.
Okay, I'll try it.
All right. Are people here still filling out attendance? Can you raise your hands if you're still doing that? All right, looks like we're clear, so I'm turning it off. Okay. So now we're ready to talk about logistic regression. All right, so I've talked to you about the intuition behind it. I've given you the sigmoid function. And so what I can do now is define the model and the loss function that we use for logistic regression. Okay, so the same framework as linear regression in that we pick a model and we pick a loss, and we fit that model using gradient descent. But this time, both the model and our loss will change. So our model now is the sigmoid of theta.x instead of theta.x on its own. And the sigmoid here you can imagine as saying, take our regression and make it predict probabilities instead of predicting any real number. Okay? What I'm going to do now is just abbreviate one prediction as z sub I. And the reason for that is because the next loss function is kind of complicated. It looks like this. Okay, so the loss function we use for logistic regression is what we call the cross-entropy loss. Don't feel scared if it looks intimidating. I'll try to walk slowly through it on the next few slides. But the takeaway here is that even though my model and my loss are more complicated than what we're used to seeing, we can still use them and we can still fit gradient descent with them. And you can still understand it if you spend some time like really trying to dig into how these different functions behave. Okay, so right here I've abbreviated our predictions as z sub I. But how you should read this is z sub I are our predictions for y. And the reason why I've done that here is just to avoid like having tons of parentheses and bolded letters in this equation. Okay. All right, and as before with linear regression, we can tack on a regularization term to the loss function and have our thetas be regularized. Okay. Now, our model here predicts a probability, right? It predicts a probability that y is 1 given x. But for classifiers, oftentimes we want to predict a category, not a probability. So we want to say whether the shot will make or miss, not whether the probability of making is 0.5. But to go from a probability to an actual decision or a classification, it's not super hard. Basically what we'll do is we'll make a decision rule. Okay? So if our predicted probability is 0.5 or more, then we'll predict 1. And if it's less than 0.5, we'll predict 0. And that way we can convert from probabilities to actual categories. Okay, so what I've done here, again, is we started off with classification, and then we kind of tweak the problem until it looks like regression, and then we can solve the problem for regression, and then now we're going back to classification. Okay. I want to take a closer look at this cross-entropy loss here. Okay. Let's take a look. Here we go. Okay, so what I have here is a toy data set of x's and y's. Okay, and we can see here that if you're below -2, you're probably going to lose a game. If you're greater than 1, you're probably going to win the game. But these don't really have any meaning. I just have some data here to plot. Okay. And what I can do is plot for you just a basic sigmoid function, plot on top of these points here. Okay, and the question is, is this model a good fit for the data? And to answer that question, what we want to do is to find some sort of way to determine the goodness of this function. Just like how for linear regression, we try to write a loss function to determine how good that line was from the points. For logistic regression, we can define a similar type of loss function to determine how good our curve is for these points. Okay, and so one thing you might want to do is you might say, okay, well, the squared loss seems like a pretty good idea. Why don't we just use the squared loss? So we can try doing that. Here we go. So what I'm going to do here is this is the empirical risk, which is also known as the average loss. The reason why I'm switching back and forth between names of things is because in real life, you'll have to switch back and forth between names of things. Okay, so in real life, you'll see empirical risk, you'll see average loss. People use them interchangeably, and so I will too, so you can get some practice seeing that vocabulary. Okay, so I have here, the loss is my x values times theta, or my predicted values is my x values times theta, and my loss is the mean of, let's see here, the loss function applied on my data, on my predictions, sorry. Let's do that. For y hat. You know what? I can just do this. Let's do that. Okay. And the squared loss here is y minus y hats squared. So relatively simple, and I made a mistake. Hello. What's going on here? This should be toy y. So my actual y values compared with my predicted y values. Okay, here we go. So what I plotted here is the loss curve. The loss curve says, here are a bunch of different theta values to try, and here is the loss for each particular value of theta on all the points. Okay, so we can see here that if I set theta equal to 0.5, we have a low loss. If we set theta if you set theta equal to -2, we have a pretty high loss for the mean squared error. Okay. But it turns out that this function is not convex. How do you know it's not convex? You can try drawing a line, right? And if the function goes above that line, then it's a non-convex function. And we can see here that if I draw a line between these 2 points in the curve clearly goes above this line that I'm tracing with my mouse here. And it turns out that if you run gradient descent on the mean squared error loss for logistic regression, you can sometimes get the right answer, but other times you won't get the right answer. Okay, so one reason why we use the cross-entropy loss instead of the mean squared error is because the cross-entropy is convex. There are other reasons too, but this one is like perhaps the most easy. It's probably the easiest to understand based on what we've talked about in this class. Okay. So let me give you some intuition around the cross-entropy loss function. It's not just some made-up, like magical incantation of variables. It does have some meaning. And the meaning here is, if our model makes a prediction, that prediction, we can label it p hat. Okay? And we can, in particular, we can like tweak our prediction a bit so that p hat is our predicted probability of the correct class for the individual, which essentially means that what we're asking is what's the chance that our model got the answer right? Okay, so if our point here is at 0, we might be concerned with how close our model will get to 0. And if our point here is at 1, we're concerned with how close our model gets to 1. Okay, so for the points that are 0, we would like our model to be close to 0. And for the points that are 1, we would like our model to be close to 1. That's the basic idea here. Okay. And so the idea here is that p hat is a chance of being right. And so we can kind of develop some intuition around what we think our loss function should behave like. All right? So we say that if p hat is equal to 1, that means that we're going to be right. That means our model is exactly right. If our model is exactly right, our loss should be 0. If p hat is close to 1 but not quite 1, then our loss should be pretty low. Our loss should be small. But if p hat is low, which means our model is pretty far off from the real point, then our loss should be large. Okay? But whatever p hat is, our loss should be non-negative, because we want positive or 0 or positive losses. And it turns out that if you take the negative log value of a probability, you fulfill all these conditions at the same time. Let me show you why. Okay. So what I have here is p hat, the predicted chance of getting the right answer. Okay, so a 1 here means that if the point was at 0, my model predicted exactly 0. Or if the point was at 1, my model predicted exactly 1. As I go left on the x-axis, my model gets further and further away from the real value. Okay, so if I go really far away, I get a really high negative log value. And if I go all the way to 0, I get basically an infinite loss. Okay, so that's the intuitive idea here. And it turns out that if we take our original points and look at the p hat values, then what we can see here is we can say, okay, well, for this point here, this point was at 0, our model basically gets 0, so that's good. We'll mark that as a yellow bar. This is a yellow bar. And so our p hat values are the lengths of these lines here, right? So for this blue point here, our model predicted point 3, but the real point was all the way at 1. So this right here should incur a large loss. Okay, so what I've drawn here is just the predicted probability of each point. Okay, and the idea here is we can take the negative losses of all of these lines and add them all up. Okay. This actually gives us the cross-entropy loss expression. And the reason why it gives us the cross-entropy loss expression is because what we're saying here is, okay, this term right here, so yi is always 0 or 1. Right? So y sub I refers to our actual data points. And if y sub I is 1, then this term right here will be 1. But this term right here will be 0, because we're doing 1 minus 1, which is 0. If y sub I is 0, then this term right here will be 0, but this term right here will be 1. Okay, so we're essentially flipping back and forth between these two terms. And for every term, what we're doing is we're taking the negative log of the probability that our model got the right answer. And I'll give you some practice with this to try to wrap your mind around it. But basically the idea here is this expression here is a measure of how close our model predictions are to the real points. Okay, so let's code it up. Coding it up is not too bad. So this is -y times np.log hat minus 1 minus y times the log of 1 minus y hat, like so. Okay, and what I've drawn for you here is again the loss curve, but this time we can see that the loss curve is convex, or at least the portion that we can see on this plot is convex, but I'm going to tell you that the rest of the function here is convex too. So if we run gradient descent on this particular loss function, we're going to get the correct value of theta as long as we converge. Okay. So I talked about the model, and I talked about the loss, and I want to go over them again just so we can try to cement these ideas in our minds. Okay, so why use the sigmoid function? The sigmoid function arises from assuming that the log odds ratio is linear, which essentially means, once again, that the probability of 1 divided by the probability of 0, the log of that ratio here is a linear function in theta. Okay? If you do algebra, you can recover this particular expression here, which is the sigmoid function on a particular value. It's on the value x dot theta. Okay. Now to give you some intuition on this, the theta in the sigmoid function feels like the quote-unquote slope of the logistic model. What I mean by that is, if I increase theta, right, my slope seems to get higher. It's not really a slope here, right? But it looks like the slope of this portion of the graph gets sharper and sharper as I increase theta. If theta is negative, then we go from high to low, and if theta is positive, we go from low to high, just like how if we have a positive slope, we go from low to high, and if a negative slope for a line, we go from high to low. So it feels like the slope of a logistic model. It's not exactly the slope. I'm just trying to get you to kind of like see how theta affects the predictions of our model. Okay. All right. And I also showed you the cross-entropy loss. This is the loss that we typically use for logistic regression. But it turns out that squared loss is not actually a terrible choice. In the past, it was used quite often, and it's still used from time to time today. Although in this class and in the classifiers that you'll probably see in the real world, almost all of them will use the cross-entropy loss. It does get you like pretty close to, it does get you a good model a lot of the times, but it turns out that the empirical risk function can be non-convex. So it can be tricky to minimize if you don't if you don't put in a lot of effort to minimize it. Okay, and it turns out that this cross-entropy loss has a motivation based on probabilities, but it also has a lot of other motivations. One of them is the maximum likelihood motivation, and the other one is the minimum KL divergence motivation. If you look in the textbook, I think we have an explanation of KL divergence, but we decided that this summer it's probably okay just for you to know this loss function and to know how it behaves, as opposed to knowing the motivations. You'll learn about the motivations probably in 102. So I suspect in 102, they'll go over the maximum likelihood explanation for this loss function. Okay. So let's get some practice. Huh. Oh, here we go. Okay. So here's a loss, the average loss. And as usual, I use little l to refer to the loss on a single point. And what I'd like for you to do now is suppose that we only have one feature and no intercept. If theta is equal to 2, please compute the single point losses for these 4 points that I have here. Okay, so I have here the point 5, 1, 0, 1, 0, 0, negative 1, and 1. Okay, so try plugging in these numbers into the model to see the model's predictions, plug it into the loss to compute the little l loss for each of these points. If you want a challenge, you can think about if you're running stochastic gradient descent, in which direction would the algorithm update theta? So will it update theta in the positive direction or the negative direction for each of these points here? Okay, so try it out. All right. If you're finished working on those problems, go ahead and compare answers with your neighbor, see if you get the same numbers, and see if you agree on the directions of updating for each theta. Okay. Let's go over these ones. I give you these to give you some intuition on how this entropy loss behaves. The only real way to get some intuition around this is to actually practice like manipulating it, plotting it, plugging in some numbers and seeing what you get out. And so here we go. We have the loss and we have theta equals 2. Okay, so for the first point, our prediction for that point is x times theta passed into the sigmoid function, which is about equal to 1. So the prediction here is sigmoid of 5 times 2, which is equal to 1. And since our original point was also 1, our loss is basically 0. It'll be a very small number. It won't be exactly 0, but it'll be almost 0. Okay? It makes sense because if theta is 2, right, our sigmoid function goes from low to high, and the x equals 5 here is pretty far out on the x-axis, or the sigmoid of 10 here is really far out on the x-axis, and so our sigmoid of that function will be almost 1, and because our prediction here closely matches the actual value in the point, our loss will be almost 0. Okay. All right, second point. We have here 0 and 1. Our prediction here is 1/2. It turns out that our prediction for the x value 0 will always be 1/2, no matter what theta is. Think about that if you don't quite understand. Okay, our prediction is 1/2, and so our loss for that particular point is plugging into the loss formula. We have here -1 times the log of 1/2 minus 0, because 1 minus 1 is 0. And so we get 0.693. It turns out that for 1, 1, we get the same loss. Why do we get the same loss? It's not just because the numbers here come out the same. It's also because our sigmoid function always passes through the point 0 and 1/2. Okay, so if I go back here, let's look back at the sigmoid function. All of these functions pass through the 1/2 mark when x is equal to 0. And so the distance from 1/2 to 1 or -1 is the same, and therefore the loss should be the same. Okay. For -1 and 1, this right here is more of a plug and chug, so you pass in -1 and 2, we get a low probability. And our loss here on that particular point is relatively high, 2.129. Why is it higher than the others? It's higher because our model's prediction is pretty far off from the actual value. Our model predicts the probability is low. It's below half. But our actual point is at 1. Because of that, our loss is high. Okay. Notice how one term in the loss is always equal to 0. Okay, so that's the behavior of the cross-entropy loss. And the reason why one term in the loss is always equal to 0 is because either y sub I will be 0 or 1 minus y sub I will be 0. Y sub I will be 0 when y sub I is 0, and 1 minus y sub I will be 0 when y sub I is equal to 1. Okay, and since y can only be either 0 or 1 of these terms will always equal to 0. Sorry, could you say that again? Is the third line 4.00? Did I write that wrong on the last line? I put 0, 0? Did I not write that here? Oh, my bad. It should be 0, 0. I apologize. Yes, so this right here should be 0, 0. Good catch, thanks. Okay. When I run stochastic gradient descent on these points, what direction will theta move in? I'm going to tell you, but you should think about why they move in these directions. Okay, so for the first one, theta will move in the positive direction by a very small amount. For these two, theta will also move in the positive direction, but by a larger amount. And for the last point, theta will move in the negative direction by a large amount. See if you can figure out why. But I'll leave you with that as an exercise. Okay. So we can put it all together. Oh my gosh. Put it all together. Let's go back down here. All right, so we have here our games table. And what we want to do with our games table is predict the one column from the difference in field goal percentage, in difference in proportion of shots made. Okay? So what we can do is, I'm going to plot for you again the one versus the field goal difference. So we see here, as you make more field goals than your opponent, you're more likely to win. And what we can do here is define our model. Our model for logistic regression is the sigmoid function applied to the field goal percentage difference times theta. Right? And our empirical risk for our model is our predictions on theta. We'll take our actual values from our data set, the one column, and we'll return the average of the cross-entropy loss, which is negative y times the log of y hat minus 1 minus y times the log of 1 minus y hat, like so. Okay, so this is our average loss on our data set, or our empirical risk. What I can do here is I want to minimize our risk. And to minimize our risk, optimize, I can import a minimizer function from SciPy, and I can say, let's minimize our risk. Using a theta value, we'll just guess a theta value of 1 to start. Okay, so what this does underneath the hood is run a version of gradient descent to minimize the risk, and it found that the best value of theta is 30. So remember way back in this demo, I showed you how, like, if I plot something times 30, we get the curve that just happens to match our data pretty well. And it turns out we get the same number here when we run gradient descent on our data. Okay, so we get here the value 30. And to show you this plot again, I can take this and take out the x attributes and take out the number here, and this is the number 30, 30.558 roughly. I can take our win rates, plot them, and I can also take our model's predictions and plot them as well. So here are our field goal percentage differences. Here is my model's predictions, because I take the x values and multiply by theta. And we see here that our model's predictions match the binned proportion of games won quite well. So that's logistic regression. Okay, so as a fun aside, it turns out that when it comes to modeling, we're often interested in whether or not we make the right prediction. But sometimes it turns out that making the wrong prediction can be of value if you look at why you got the prediction wrong. And in particular, sometimes the wrong predictions are the most interesting ones. And I'll show you a shot that just happened a few months ago in the NBA. Let's see if this plays. It's my favorite player, Kawhi Leonard. And this is like the game-winning shot. Is the sound on? Oh my gosh, it's so much better with the sound on. All right, let's try that. Oh my gosh. So here he is. His team's fate is on the line in the shot, and it's still not on. Why though? Okay, well, I have my sound plugged in. If it doesn't work, you just have to watch it at home, sadly. All right, let me give it one more shot. Sound is on. External MacBook Air speakers. Does that work? Let's do that. Turn my laptop volume on. All right, one more time. If it doesn't work this time, we'll call it a day. All right, no sound. But anyway, he's guarded by 2 players, okay? The shot bounces like 4 times. It goes in. His team wins, and everyone's really happy. I was pretty happy when I saw this. My family doesn't watch basketball, so they didn't understand why I was shouting, but I was shouting. I was excited. Okay. But anyway, if you look at everything about this shot, it looks like there's no way it's going to go in. Because he's guarded by like he's guarded by a really tall guy. The ball bounces like 4 times. He shoots it from like way off like the court. But it manages to go in, and his team ends up winning the championship. So in any case, it's just a fun. There's not really a connection to the material. I just want to show you this shot. All right. Talked about classification. We talked about logistic regression. And again, the wrong predictions can be the most interesting ones. I'll see you tomorrow.